Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do an example of using the integrating factor to solve a differential equation. And this is an initial value problem because notice we have our differential equation and we're given an initial value. Okay, so we want to solve y primed plus 2y equals e to the x, given also y of 0 is 1. So how do we do this using integrating factors? Well, what is the integrating factor? Well, it's a function mu of x, so Greek letter mu, mu, and we're going to multiply this. Well, first we're just going to call it mu for short, and then we're going to multiply both sides of this equation by mu. Okay, so let's go ahead and do that. So what we're going to get then is mu y primed plus 2 mu y equals mu e to the x. Okay, now the idea is we want mu to be a function so that this left-hand side can actually be expressed as the product mu y primed. Okay, so we want mu to be some suitable function so that if we take the derivative of this product, then we end up with this. But what is the derivative of this product? If we use the product rule, then we know that mu y primed from the product rule is going to be mu y primed plus mu primed y. Okay, so basically then the idea is that we want mu to be a function so that, well, notice also mu y primed, we want it to be equal to this. So what we're actually going to have then is this equals mu y primed plus 2 mu y. Well, so let's start matching things up and see what we can determine about mu. So here's mu y primed, that's great, those match up perfectly. Here's a y, those match up. So what's left then is this mu primed has to be equal to 2 mu. So in order for mu to be a suitable function so that this can be expressed as mu y product primed, then we need to have mu primed equal to 2 mu. So we need mu primed equal to 2 mu. Okay, and this is an elementary differential equation here, and right away we can say that this tells us that mu equals e to the 2x. Now, technically speaking, there should be an arbitrary constant in there, but we don't have to worry about that because it would just be absorbed into the arbitrary constant from the original equation anyway, and that arbitrary constant is actually going to be determined by the initial condition. So again, we don't have to worry about the arbitrary constant here because it just gets absorbed and then ultimately it just gets determined by this. Okay, so if mu primed is 2 mu, then mu equals e to the 2x. So this function here is our integrating factor, and we want to multiply both sides of this equation by that. Now, how does that help us? Well, let's go ahead and go to the next page. So we have mu y primed plus 2 mu y equals mu e to the x, and we wanted a mu, we actually just found a mu, so that the left-hand side is actually equal to mu y primed. Now what we can do is integrate both sides. If we integrate both sides with respect to x, then what? Well, on this side, if we integrate mu y, that product prime, we just get mu y, right? And then what happens over here, because we're just integrating a derivative, so if you integrate the derivative, you just get this thing back. And then over here, we still actually just have this mu e to the x dx, and then divide both sides by mu, and then we end up with an expression for y. So y is 1 over mu times the integral of mu e to the x dx. And remember, we already found mu, it's e to the 2x. So we can just take this and stick it into this formula here, and then that gives us our y. So again, how did this all work? Well, we started by multiplying both sides by mu and said, okay, we want this mu to be a suitable function so that this is actually equal to this. And the only way that's going to work is if mu primed equals 2 mu, because everything else already matches up with something else. Well, if mu primed equals 2 mu, then that means mu equals e to the 2x. And we ignore the arbitrary constant because it just gets absorbed and determined later. So if mu is, well, and then stepping back a bit, how does this mu even help us? Well, if we can express this as mu y primed, then we end up with mu y primed equals mu e to the x, and then we integrate both sides, and then we got this. And then remember, if you integrate the derivative here, you just get the expression back. And then over here, we have to leave that as it is, and then divide both sides by mu to get where we are now. All right, and again, because we actually have the mu, we know that mu is e to the 2x, then we can figure out what y is explicitly. So y equals 1 over e to the 2x times the integral of e to the 2x times e to the x dx. 1 over e to the 2x, we can just write that as e to the negative 2x. And then this is the integral of e to the 2x plus x, which is e to the 3x dx. And then this equals e to the negative 2x times, now we have to be careful here, if we integrate e to the 3x, we get 1/3 e to the 3x. And now we have to remember our arbitrary constant. So we have this so far. All right, so let's go ahead and go to page 3, and then what we have now is y of x equals e to the negative 2x times 1/3 e to the 3x plus c. All right, that's what we have so far. Now, let's go ahead and distribute this e to the negative 2x just to simplify a little bit. So we end up with 1/3 e to the negative 2x plus 3x is just e to the x. Then we have plus c e to the negative 2x. All right, and then don't forget, we have our initial condition, y of 0 is 1. So that's going to help us determine this arbitrary constant c. So if we know that y of 0, if we know that y of 0 is 1, let's plug 0 in for x into this formula here and see what we get. So using the formula, we have y of 0 is 1/3 e to the 0 plus c times e to the 0. E to the 0 is just 1, so this is 1/3 plus c. Okay? Now, if y of 0 is 1 and y of 0 is 1/3 plus c, then 1/3 plus c has to equal 1 because both of these guys equal y of 0. Okay? So then what we have is 1/3 plus c equals 1. Subtract 1/3 from both sides, and we get c equals 1 minus 1/3, which is 2/3. All right, and then finally, that gives us the final answer, which is y of x equals 1/3 e to the x plus 2/3 e to the negative 2x. And there are many, many, many different ways to write this formula here, but we'll just stick with this. So y of x equals 1/3 e to the x plus 2/3 e to the negative 2x. And it really wouldn't hurt to verify this, that this equation actually solves, or excuse me, that this function actually solves the differential equation by taking a derivative, plugging everything into here, and checking that both sides, the two sides equal each other, and verify that this is satisfied as well. So anyway, this has been an example of using the integrating factor to solve a differential equation. I hope you found this video helpful, and thank you for watching.